Hello everyone. Let us continue with the GATE Aerospace 2024 paper solution. This is faculty advisor from the JNFF Academy. Now let us see the question. This question is from the thermodynamics part, which says for an ideal gas, the specific heat at constant pressure is 1147. What is given? Cp is given. That is given Cp is equal to 1147 joule per kg Kelvin. And the ratio of specific heat is also given, that is gamma is equal to 1.33. What is the value of gas constant for this gas is, that is R it is asking, that is gas constant. So we know the relation between Cp and Cv as Cp minus Cv is equal to R. We don't know Cv. To find Cv we can go with the specific heat ratio. Cp by Cv is equal to gamma. From here we can find Cv, that is Cp by gamma. Cv is equal to Cp is 1147 divided by 1.33. If you do so, we will get the value of this as 862.4 joule per kg Kelvin. We have found the Cv as 862.4 joule per kg Kelvin. Now let us substitute this value and get the answer. Cp minus Cv is equal to R. Cp is 1147 minus Cv is 862.4 is equal to R. If you subtract, we will get R as 284.6 joule per kg Kelvin. This is the answer for this question. Out of the given option C is the correct answer for this question. To know about more such concept, contact JNFF Academy. Thank you. Hello everyone. Let us continue with the solution part of GATE Aerospace 2024 paper. This is faculty advisor from the JNFF Academy. This question is from the propulsion part, which says a surrogate liquid hydrocarbon fuel approximated as C10H12 is being burned in the land-based gas turbine combustor with a dry air, that is 79% of nitrogen and 21% of oxygen by volume. How many moles of dry air are required for the stoichiometric combustion of surrogate fuel with a dry air at atmospheric temperature and pressure? We need to burn this fuel, that is C10H12 has to be burned with a dry air, that is O2 plus 79 by 21 N2, which releases CO2 plus H2O plus 79 by 21 nitrogen. We just need to balance this equation. How many carbons are there? Here it is 10, then I multiply with this at 10. How many hydrogens? 12 hydrogens. So I need to multiply here with 6. Now oxygen needs to be balanced. So here it is 20 oxygen plus 6, 26 oxygen. So I should be multiplying here with 13. 13 into 2 is 26. Now the equation is balanced. Here it should be multiplied with 13. This equation is perfectly balanced. So how many moles of dry air is required? That is 13 moles. Out of the given option, which option is correct? Option A is correct for this question. To know about more such concept, contact JNFF. Hello everyone. Let us continue with the solution part of GATE Aerospace 2024 paper. We are solving the jet propulsion part. The question here it is says, an aircraft with a turbojet engine is flying with a speed of 250 meter per second. Speed of the flight is 250 meter per second at an altitude where the density of air is 1 kg per meter cube. At that altitude, the density is given, that is 1 kg per meter cube. The inlet area is also given, that is AI is equal to 1 meter square. The average velocity of the exhaust gas at the exit of the nozzle is, exit velocity is also given, that is 550 meter per second. Assuming the engine exit pressure is equal to ambient pressure, P exit is equal to P ambient, and neglecting the fuel to air ratio, that is F is negligible. Now what we need to find? The uninstalled thrust produced by the engine at this condition is, in Newton we need to find, round off to the nearest integer. The thrust we need to find. Thrust at T is equal to, we know m dot A 1 plus F V exit minus V ambient. Since P exit is equal to P ambient, pressure thrust is neglected. Thrust T is equal to m dot A. Since F is also negligible, V exit minus V ambient. We don't know m dot a. Let us first find m dot a. M dot a is nothing but density of the air, speed of the flight into area at inlet. 1 into 250 into 1. So mass flow rate of air is 250 kg per second. This is the mass flow rate of. Let us substitute and get the thrust. Thrust T is equal to 250. V exit is given as 550 meter per second minus 250 meter per second. So this thrust T is equal to 250 into this is 0, 0, 300. If you multiply this, you will get as 75,000 Newton. What is the answer? The integer is 75,000. That is the answer is 75,000 Newton. This is the answer for this question. To know about more such concept, contact JNFF Academy. Thank you. Here is yet another question which says, in an air breathing gas turbine engine, the combustor inlet temperature is 600 Kelvin. Let us consider this as combustor where inlet temperature T01 is equal to 600 Kelvin. The heating value of the fuel is, that is CV of the fuel is 43.4 into 10 power 6 joule per kg. Assuming Cp to be 1100 joule per kg Kelvin for air and the burned gases. Cp for air and Cp for gas is equal, that is 1100 joule per kg Kelvin. The fuel air ratio is very smaller than 1. Neglect the kinetic energy at the inlet and exit of the combustor and assuming burner efficiency to be 100%. This is burner efficiency is 100%, it is given. What is the fuel air ratio required to achieve the outlet temperature of the combustor exit is? How much outlet temperature we want? We want to have outlet temperature, that is T02 is equal to 1300 Kelvin. So we know fuel to air ratio can be obtained, that is Cp of gas outlet temperature minus Cp of air inlet temperature divided by burner efficiency into heating value of the fuel minus Cp of gas into outlet temperature. Since Cp is same for gas and air, so we will take Cp of gas outside, T02 minus T01 divided by burner efficiency is 1, so heating value of the fuel minus Cp of gas into T02. Let us substitute the value and get the answer. That is F is equal to Cp of gas is given as 1100, outlet temperature is 1300 minus 600 divided by 43.4 into 10 power 6 minus, this is Cp of gas is 1100, outlet temperature is 1300. So if you do the calculation, the upper part you will get as 7740 divided by 43, at the bottom you will get denominator 43.39 into 10 power 6. If you divide the calculation further, you will get the answer as 0.0177. This is the fuel to air ratio. Out of the given option, which one is correct? Option A is correct for this concept. To know about more such concept, contact JNFF Academy. Thank you. Hello students, let us continue with the solution part of GATE Aerospace 2024 paper. We were solving the jet propulsion part. Here the question says, centrifugal compressor is designed to operate with air. At the leading edge of the tip of the inducer, the blade angle beta is given as 45 degree. The relative Mach number relative is 1. Stagnation temperature at the inlet is T01 is equal to 300 Kelvin. Consider gamma equal to 1.4. Neglect preval and slip. The inducer tip speed is, that is u we need to find. Let us draw the velocity triangle as per the given data. This will be the velocity triangle. This is absolute velocity, this is relative velocity, and this would be the speed, that is u. So this angle is given as 45 degree. This W can be resolved into two components, that is W cos 45 is equal to C, W sin 45 is equal to U. Since the question is talking about the relative Mach number, let us start with that. Mach number relative is equal to relative speed divided by square root of gamma RT, which is equal to 1. From here we can obtain the W as square root of gamma RT. Let this be equation 1. Take this square one side, then you take this equation as 1. So this is gamma RT equation 1. So static temperature is not given. From stagnation temperature, let us obtain this. So T is equal to 300 minus C square divided by 2Cp. So T is equal to 300 minus C in terms of W we know as W square cos square 45 divided by 2 into 1005 Cp for air. So let's substitute and get the values. T is equal to 300 minus W square, this would be 4 into 1005. Let us call this equation as 2. Now substitute 2 in 1. What we will get? W square is equal to gamma R 300 minus W square divided by 4 into 1005. Now when you multiply this gamma R inside, what we will get? W square is equal to 120540 minus 0.1 times of W square. When you take this W square this side, we will get 1.1 times of W square is equal to 120540. From here we will get W as, take the square root, we will get the W as 331.03 meter per second. But what we want U, which is U is equal to W sin 45. That is nothing but U is equal to 331.03 divided by root 2. That is U we will get from here as 234 meter per second. This is the correct answer for this question. That is U is equal to 234 meter per second. To know about more such concept, contact JNFF Academy. Thank you. Hello students, let us continue with the solution part of GATE Aerospace 2024 paper. We were solving the jet propulsion part. This question is from the axial flow compressor. The question says a multi-stage axial compressor with overall efficiency is 0.83, that is compressor efficiency is 0.83. It is used to compress at a stagnation temperature of 300 Kelvin. T01 has given 300 Kelvin. Pressure ratio is pi c is nothing but 10:1. Each stage temperature rise across stage as 20 Kelvin. The Cp of air and gamma of air is given as 1005 joule per kg Kelvin. Gamma of air is 1.4. How many stages are there in this compressor? Number of stages he is asking. So we know total temperature rise across the compressor is equal to number of stages into temperature rise across the stage. So we need to find total temperature rise across the compressor. From the efficiency of the compressor, we can find that T02 dash minus T01 divided by T02 minus T01. This is the temperature change across the compressor. That is delta T0 is equal to, this is if we take T01 as common, so this will be pressure ratio power gamma minus 1 divided by gamma minus 1 divided by efficiency. Let us substitute the value and get the temperature change across the compressor. That is 300 Kelvin into 10 power 0.4 divided by 1.4 minus 1, this whole divided by 0.83. When you substitute this value and calculate, you will get the temperature change across the compressor as 336.39 Kelvin. To find the number of stages, this is should be equated 336.39 should be equated n into 20. When you calculate this n, you will get nearly about 16.8, which is almost equal to 17. So answer for this question is option B, 17. To know about more such concept, contact JNFF Academy. Thank you. Hello students, let us continue with the solution part of GATE Aerospace 2024 paper. As we were solving the jet propulsion part, this question is from the rocket propulsion, which says a chemical rocket with ideally expanded, which means what? P exit is equal to P ambient. The nozzle produces a thrust of, that is, it produces a thrust of 5 into 10 power 6 Newton at sea level. Specific impulse of the rocket, that is ISP, is equal to 200 seconds, and acceleration due to gravity, that is G, is equal to 9.8 meter per second square. The propellant flow rate of the rocket nozzle is, we need to find m dot p. Since the nozzle is ideally expanded, so thrust is equal to mass of the propellant into V exit. So there would be pressure thrust P exit minus P ambient into area at exit. Since it is 0, so thrust would be equal to mass of the propellant into exit velocity. So we know ISP is equal to force thrust divided by mass of the propellant into acceleration due to gravity. So ISP, it is given as 200 is equal to thrust is nothing but 5 into 10 power 6 divided by mass of the propellant we need to find, G is nothing but 9.8. When we solve this, we will get this answer as 5 into 10 power 6 divided by 200 into 9.8, which is nothing but m dot p is equal to 2551.0 kg per second. That is, answer for this question is, round off to nearest integer is 2551 kg per second. This is the answer for this question. To know about more such concept, contact JNFF Academy. Thank you. Hello everyone, let us continue the solution part of GATE Aerospace 2024 paper. As we were solving the jet propulsion part, this is the one of the question out of it. An aircraft with a turbojet engine is flying with 250 meter per second. Speed of the aircraft is, that is 250 meter per second. The uninstalled thrust produced by the engine is 60,000 Newton. Heating value of the fuel is, that is CV, is equal to 44 into 10 power 6 joule per kg. The engine has thermal efficiency of the engine is 0.35, that is 35%, while the fuel flow rate is, that is m dot f is equal to 3 kg per second. Assuming the exit pressure to be is equal to ambient pressure, what we need to find? We need to find the propulsive efficiency, that is eta p we need to find. We know that the thermal efficiency is equal to propulsive power divided by fuel power, that is propulsive power divided by fuel power is nothing but m dot f into heating value of the fuel. From here we will get propulsive power as thermal efficiency into m dot f into heating value of the fuel, and we know the propulsive efficiency as thrust power divided by propulsive power, which is nothing but F into VA divided by thermal efficiency into m dot f into CV. Let us substitute the values and get the propulsive efficiency. F is nothing but 60,000 Newton into 250 divided by 0.35 into 3 into 44 into 10 power 6. When you Do this calculation. You will get the answer as 0.3246, which is nothing but propulsive efficiency is nothing but 32.46. Out of the given option, which one is correct? The option is correct for this question. To know about more such concept, contact JNFF Academy. Thank you.